Jai Gurudev student. Today we'll take hybridization. Hybridization is actually intermixing of atomic orbital. Intermixing of atomic orbital. Intermixing atomic orbital of almost equal energy to get hybrid orbital of equivalent shape and energy. So if you have intermixing of atomic orbital is called your hybridization. For example, if you want to prepare chapati, then you have to add your wheat, salt, water, oil. These are all different energies, but when you intermix them and prepare the balls having the equivalent shape and energy. So this is what is called hybridization. Hybridization nothing but intermixing of atomic orbital. Atomic orbital means what? 1s, 2s, 2p. These are your atomic orbitals. If you have intermixed them, you will get the hybrid orbital. Now salient features of hybridization. In features of hybridization, point 1, orbitals of almost equal energy take part in hybridization. Now if I have 2s, 2p, 3s, 3p, 3d, then 2s and 2p undergo hybridization, 3s, 3p, 3d hybridization undergo hybridization. This is possibility, this is possibility. Now if you want to hybridize to 1s and 3s, it is not possible because their energy is different. So hybridization is nothing but intermixing of atomic orbitals of almost equal energy. Now second point is that number of hybrid orbital is equal to number of atomic orbital intermix. And how many hybrid orbital you get means how many atomic orbital you have intermixed. For example, if I have nitrogen, so this is 1s2, 2s2, 2p3. Now this is the valence shell. Is another point, remember, only valence shell involved in hybridization. Now this 2s and 2p is the valence shell. If I draw the box diagram for 2s and 2p, it will be like that. This is 2s2, this is 2p3. Now this valence shell, this one is your valence shell. So valence shell means this one is valence shell, 2s and 2p is the valence shell, means outermost shell. The outermost shell undergo hybridization. So there is one s orbital involved in the hybridization and 3 p orbitals involved, s1 p3. So this is the hybridization type is s1 p3 type. Now another point is geometry is indicated by the types of hybridization. Geometry also depends on hybridization. Geometry is depends on hybridization. Type. Now if the hybridization type is your sp3, means how many orbitals are there? 1, 2, 3, 4. Then geometry will be like that. sp3 is tetrahedral. Now you can remember the BSc pair theory. From that one also, if there is 4 is there, this becomes tetrahedral. So geometry depends on types of hybridization. If it is sp3, then we have tetrahedral. If we have sp2, trigonal planar, sp is linear. So this type of geometry depends on types of hybridization. And another one, this is point we should discuss. that only valence shell promotion of electron is not a necessary condition. I am writing promotion of electron or electrons is not a necessary condition prior to hybridization. Prior to hybridization. Now promotion of electron means what? If I have a electronic configuration like that, C6, so 1s2, 2s2, 2p2. This is 2s2, this is 2p2. Now if there is a vacancy is there, then you can promote an electron. And in that case this become necessary, and in some cases in nitrogen what we have done earlier, this is already there is 2 electron in the first one and the 3 electron in the second one. There is no vacancy. If you take 1 electron, that become paired up, this become more unstable. So promotion of electron is not required here. Here promotion not required. Promotion not required. Promotion of electron is not a necessary condition prior to hybridization. And it is also said that sometimes this half field only undergo hybridization. It is not the case. Sometimes field orbitals electron also undergo hybridization. So these are some points about hybridization. Now we will consider some case on the basis of hybridization. First one, sp hybridization. So in sp hybridization, percentage of s character is 50% and percentage of p character is also 50%, because s and p, it will be shared, full 100% share will be 1s and 1p, so that will be your 50% each. Now in sp hybridization, if we have a s orbital like that one p orbital will be like that. This is sp hybridization. So atomic orbital, number of atomic orbital is 1 plus 1 equal to 2. Number of atomic orbital is 1 plus 1 equal to 2. The number of hybrid orbital will be also 2. But the number of atomic orbital is always equal to the number of hybrid orbital. And shape of the hybrid orbital is always like that. This is one hybrid orbital, this is another hybrid orbital. These are the two hybrid orbitals. Now these two hybrid orbitals, when they form for a atom, they will be look like that. One hybrid orbital like that and another hybrid orbital will be like that. So these two hybrid orbital gives you the sp, one s and one p. So this is your sp hybridization. Now we are taking one example on that basis. For example, we are taking BeCl2. BeCl2, so I will do that one. Beryllium electronic configuration 1s2, 2s2, 2p0. So this is your 2s2, this is your 2p0. Now beryllium, because there is 2 Cl atom, we require 2 orbital. So 1 electron promotion is required. So beryllium star, when you do promotion you have to write beryllium star, means excited state. 2 electron is there. So this hybridization will be your sp hybridization. Now in this sp hybridization, if you want to draw that sp hybridization for beryllium undergo sp hybridization, and sp hybridization you have to 2 orbitals, you have to draw it like that. This is sp hybridization. Now another point, that is chlorine is there, Cl is there. With beryllium we have Cl is there, so Cl 17, we know 1s2, 2s2, 2p6, 3s2, 3p5. This is your beryllium. How many chlorine? 2 chlorine, so 2 have to 2 into this. So this is 3s2 and this is 3p5. So 3p5, this p orbital left out, no? This p orbital you have to draw it like that. Another point, student, you remember here how many electron we have considered? 2 electron we have considered. So 1 electron here, another electron is here. Now the electron of this one, you have to just show it in the downward direction, there will be no problem. If it is upward, then also you can show it downward. Now 2 of them are going to join with this one to give you the final structure of beryllium chloride, and final structure will be like that. This is another, this is another, this will be the overlapping, this will be the other overlapping. Now they have shared, the 2 electrons are shared, 2 electrons sharing, you have to show it. This is your BeCl2. So similarly we can form the other ones also. So we are showing you sp hybridization we have shown, then sp2, sp3 hybridization we are going to show. Next we are taking sp2 hybridization. Obviously S percentage is 33.3%, P percentage is 66.7%. So 1:2 ratio, 100 if you divide 1:2 ratio, it will be like that. Now if I consider the example of BCl3, now BCl3 boron 5, electronic configuration 1s2, 2s2, 2p1. So this will be your valence shell. Now to mark the valence shell undergo hybridization. Now this is your 2s2, this is your 2p1. Now how many chlorine atom is there? How many chlorine atom is 3 chlorine atom is there. So you have to 3 orbitals required. So in that case you have to promote 1 electron into this one. So after that its structure will be like that, 1, 2, 3. This is B star. So now you have to consider the hybridization. Hybridization is 1s and 2p. So it will be your sp2 type of hybridization. So how many atomic orbitals involved? There are how many atomic orbitals involved? Atomic orbitals is 1, 2, 3. So hybrid orbital also be 3 hybrid orbital is there. So 3 hybrid orbital, you see 3 corners of a triangle like that, 3 hybrid orbital is there. And how many electrons are there? There are 3 electrons are there, so 1 electron, 1 electron, 1 electron. So 3 electrons I have put. Then from Cl17, how many Cls are there? 3 Cls are there. So 3 into Cl17, it is 1s2, 2s2, 2p6, 3s2, 3p5. So this is valence shell 3s2, 3p5. One point to remember, only central atom undergo hybridization, and these are the rest of the atoms and do not show it hybridization. This is a p5. So 1 p electron is there. So this is the 3 p electrons comes and join into this one. So this is the final structure will be like that. It's a p orbital. Another p orbital. Another p orbital. So reverse direction. So this is how the hybridization of this one. Next, we are doing sp3 hybridization. So in the percentage of S character is 25%, percentage of P character is 75%. So in this, the example is your CH4. Example is your CH4. So just see how we'll solve that one. Carbon 6, 1s2, 2s2, 2p2. So here is 4 atoms, 4 required, so 1 electron should be promoted. So carbon star. So this is your 1s and 3p involved. So hybridization type is your sp3 type, sp3 hybridization. In sp3 hybridization, we have to draw the sp3 orbital like that. sp3 means 1 plus 3, 4 orbitals. 4 orbitals how I will draw? This is 1, this is 2, this is 3, this is 4. This is a tetrahedral type. So there is how many electrons? 4 electrons. 1 electron, 2 electron, 3 electron, 4 electron. Now after that hydrogen, how many hydrogens are there? 4 hydrogen. Hydrogen electronic configuration 1s1. So it will be a circular shape. This upward electron, try to draw this one. Downward electron, how many hydrogens are there? 4 hydrogens will add in the 4 corners. So first of all you prepare this one. Then 4 hydrogen. It will be like that. This is the structure of CH4. So CH4 you can draw like that. Like that, if I want to know the hybridization in NH3, so nitrogen 1s2, 2s2, 2p3. This is the 2s2, this is 2p3. There is no excitation required because all these things are half filled. So hybridization type is your sp3, s1 p3 involved, means one box of s and three boxes of p. So this is your sp3 type hybridization. And how many electrons are there? 2 plus 3, 5 electrons. 1, 2, 3, 4, 5 electrons. 5 electrons are put like that. How many hydrogens are there? 3 hydrogen, means 1s1. It will be again circular. If we drop it like that, 3 hydrogen occupy 1, 2, 3 because this is already filled. So final structure is like that. So in the next video we'll take more hybridization. For this much for today.